All right, this is Physics 1B for November 9th, and we're going to discuss today more things about the second law of thermodynamics. We're going to talk about heat engines. I can't remember how far we got with heat engines last time. I'm going to go back and look just real quick. So at the end, we were kind of just discussing in general what a heat engine was, and we were talking about the way that a power plant works by heating up water, turning it into steam, taking the steam, turning it into kind of kinetic energy by pushing it over a turbine, and then by cooling that water again and then reusing it, you could have a cyclical process. And we refer to that as a heat engine. So we're going to say some more things kind of about heat engines today. Why is it not switching over? That's weird. What if I click on this? I think I just need to reopen OneNote. Okay. So we're going to say some more things about heat engines. We'll do a problem with heat engines. And from there, we're going to talk about the Otto cycle, which is the way that an internal combustion engine works in a car. Then we'll talk about refrigerators, which are basically devices that are designed to do the opposite of what a heat engine does, to cool things off, as opposed to converting heat into work. So they basically convert work into kind of moving heat out of a system to cool them off. Then we're going to look at basically two different statements of the second law of thermodynamics and what they mean. There's a lot of different ways to state the second law of thermodynamics, and they have their uses in different places. So we're going to talk about two of them. These two will be related to heat engines and refrigerators, and then we'll talk about the Carnot cycle, which is kind of an idealized heat engine, and look at some of the limitations of it. So that's our goal today. Just to refresh some of the things we talked about last time. Last time we talked about reversible and irreversible processes, and how they're kind of central to these thermodynamic systems. In general, irreversible processes are ones in which there is some kind of change or transfer of energy between types, and in the process, it's very difficult to get back the energy that you quote lose. A really simple example of an irreversible process is when an object is sliding along a table and comes to rest due to friction. And the idea is that when an object comes to rest, what's happening there? What's happening in terms of energy when you have an object that's sliding along a table and it comes to rest?
Its kinetic energy is being transferred to the molecules of the table.
Right. So kinetic energy basically gets converted into what we call internal energy, right? And to say really simply why we call this irreversible, so the kinetic energy is a very ordered thing where, the box is traveling along, and all the molecules are basically all moving to the right. So you have kinetic energy, and then when the object comes to rest, then what you have is that the molecules within the table here that have caused it to slow down, they kind of heat up, right? And what that means is that they're going to all be moving in random directions, but they've heated up. And some of them are moving to the right, some of them moving up, some moving down, left, right, etc. But all these molecules that are jiggling inside of this table due to the object sliding and coming to rest, it's very difficult to take that energy, all this random motion, and kind of convert it back to kinetic energy in the box, right? It's very difficult. So that's why we call it irreversible. And what we can do is we can take some of that energy, you could call it heat energy or internal energy or just heat or temperature increase. We can take some of that energy and we can find a way to use it to produce kinetic energy again. But what we're going to learn throughout this chapter is that when we do that by using a heat engine, There's always some energy that's lost, quite a bit actually, in reality. Okay, so it all really comes down to this. The second law of thermodynamics is all about the fact that this process is what we call irreversible. There are really no such thing as reversible processes. There are processes that are nearly reversible, but there's no such thing as a true reversible process in physics. At least not in our current formulation of what physics is, right? Because we can't truly control individual molecules yet, right? If somehow we could actually control individual molecules and isolate the energy of a single molecule and then convert it back into work or something like that, then we may be able to do something. But there's just so many molecules that the idea that we would ever be able to do that would certainly be some kind of far off technology. And we believe, physicists believe at least, that the second law of thermodynamics, the idea that there's no such thing as a reversible process, is kind of fundamental to physics. Because the nature of thermodynamic processes is that they involve random motion, and random motion is it's very difficult to use random motion to do things for you. Okay, so let's talk more about heat engines. So last time we kind of looked at a description of what a heat engine was. We looked at a kind of a power plant and how it operates. But we didn't really do any of the math. And, one of the things that we want to say about a heat engine is basically that a heat engine in general, what it does is it absorbs heat from a high temperature object.
And could that actually hurt you?
Heat from a high temperature, usually like a high temperature reservoir, something that provides heat. It then uses that heat to perform work. And then it expels kind of waste heat at the end of the process. I got problems spelling today. Expels. So you have a hot reservoir. This here is a picture. We're going to use these type of pictures to describe these processes. So you have a hot reservoir at temperature TH. It inputs heat into our engine. So the engine is this kind of like nebulous circle right here. The engine then does work. So work comes out of the system. This is kind of an energy flow diagram, right? It's what it's energy flow, right? So heat is a type of energy. Work is in a way related to energy. So heat comes in, the engine does work, it expels that work, or it uses that work is used to do something for us. Maybe turn a turbine, a power plant, maybe cause your wheels to move in your car. And then there's some kind of exhaust that comes out to a colder reservoir. In your car, this would be like the exhaust engine, the exhaust of your car, right? The pipe at the back of your car, where you're expelling excess kind of waste heat from the system. If you have a cyclic process, cyclic specifically means that it's a process in which the system returns to the same kind of initial state. So it's operating in cycle. Then what that means is that when it goes through its process, if it starts off with some energy, internal energy that we call U1, that at the end of the cycle, it's going to have exactly the same internal energy again. So if you go through a cycle where the temperature at the beginning is the same each time, right? That is to say, like in the case of a power plant, if you heat up some water that started off at some cold temperature, you heat that water up, and then you use the steam created to do work for you, and then that water gets cooled back again and then fed back into the system. The water is always starting off in that same liquid form, right? And And that means that in the full cycle of the process, the water returns back to where it was at the same temperature. And that means the internal energy at the end of the first process is the same as at the beginning. And so you can have a cyclic process. But what that means is that the change in internal energy for your what's called the working substance ends up being equal to 0. And we have this statement from, I always forget the way that this is written, but I believe that for the first law of thermodynamics says that the change in internal energy of a system is equal to how much ever heat comes into the system minus the work that's done, right? So if delta U is 0, that means that Q is equal to W. All right. Yeah. So for these heat engines we talk about, the amount of heat that comes in is going to be equal to the work that goes out. Actually, this isn't exactly right. This would be kind of the net heat. More specifically, kind of the hot minus the cold, so to speak, right? The net heat. So in general, so I wrote down here, in a steam turbine, TH is the flame, and TC is the cold water and air used to condense the steam. So in these type of systems, because the heat coming in is QH, then QH is guaranteed to be greater than 0. And since QC is the heat going out, then QC is going to be less than 0. And the net heat per cycle is going to be the difference between the two of them. So that's going to be, we're going to write it like this. We'll write QH plus QC, right? One's positive and one's negative. That's what we call the heat Q that's written here, right here, the net heat. And to write this in a way I think that's more understandable, we can just write it as the absolute value of the heat that comes in minus the absolute value of the heat that goes out, and say that that's then going to be equal to, according to this equation, that's equal to the work that's done by our engine. That's done per cycle. This would be done per cycle. So ideally, if you wanted to get the most work out of your engine, what could you say about these two terms right here? Obviously, you want the biggest difference you can possibly have, right? But what should QC be equal to if you want to get the maximum work out of your system? If this was an ideal engine.
It'd be like 0.
Yeah. So ideally, you'd have, yeah, exactly. QC would be equal to 0. But this is impossible in practice. If you don't believe me, you can go try. So what we're going to do is we're going to define an efficiency, because it's impossible to have no heat. So what would this diagram look like? This diagram, the way it would look would be this arrow that's coming down here toward the cold reservoir. Instead of going downwards, it would be turned to the right, and basically that. So if you think about it, the thickness. I don't need to move this around. I just want to kind of like the thickness of this piece right here, right? How thick this is from here to here. Determines kind of the size of the energy that comes in, and energy is conserved, right? So QC plus QW plus W here, as it shows in the picture, are equal to QH, right? But if QC was 0, then basically all the heat that came into your system would then be projected out of your system in terms of work. That would be a machine that would be 100% efficient. So the reality is that there's always going to be some fraction, and what we'll do is we can define an efficiency for the engine. So what would the efficiency be if you just think about it? It'd be 100% efficient if QC was 0, right? And QH was equal to W, that'd be 100%, right? But W is always going to be some fraction of QH. So how do you think we define the efficiency then? It's going to be like a ratio, right?
Is it like ratio? Yeah.
So we should have the small thing on top and the big thing on bottom, right? So the small thing is going to be W, the work done by the engine, and then we would divide by the heat that comes in, right?
Yeah.
So that's how we define our efficiency. And QH is actually always positive, so I don't really need to write these absolute value signs, but I do think it makes a little bit of sense to do so. So then another way to write this, we can use any of these formulas we have up here, but what I'll write, I'll use this one right here. This says that if I take QH minus QC, be sure to put absolute value signs on here. That's what the work done by the engine is. And then we divide that by, QH again. So really, this piece on top is what's really determining what's happening in your system. Ideally, what you want to do, as I said, is to make QC as small as possible. You want to eject as little heat as you possibly can, because if you think about it, that heat that you're ejecting from the system, it's a form of energy, right? You're ejecting it to a cold object, but just because it's cold doesn't mean it doesn't hold some kind of energy, right? The molecules themselves within that cold reservoir are still moving around. So if you could kind of prevent your system from losing all that cold, right? All that heat, in a way, that cold heat, then you'd have a really efficient system. But again, this ends up being impossible. We can also write this QH over QH is obviously 1, so you can write it as 1 minus QC over QH. So ideally, you make the system as hot as possible on the up. You want to make the kind of hot reservoir as hot as possible so it delivers the most amount of heat that you possibly can, because you want this number to be big, right? And you want QC, the amount of heat that you expel, to be small. But this is the efficiency of your engine. It's kind of a nice relationship. It's pretty simply stated. Okay, anyone have any questions? So we defined efficiency, and we're going to apply this this heat engine to an internal combustion engine, and then we're going to apply it to a refrigerator. So let's look at the internal combustion engine first. That's this picture right here. It's a really big picture. And we also have a PV diagram to go with this. Right here. I believe that looks a little better there. It's bigger. Alright, so I need this to be big enough that we can read it. But I also need to be able to write some things. So we'll just kind of leave it like that. The writing is kind of small. Okay, so this is what's called the Otto cycle. Okay, you can see that right here. It says Otto cycle. This is the process that happens inside of a car engine. Okay, so this is an internal combustion CE, so internal combustion engine in a car. This is kind of different from a diesel engine. So this is the engine that works off of just the normal gasoline that you would buy from your local gasoline store, gas station. So let's look at the process itself, and then we're going to go through and we're going to look at calculating what the efficiency of this engine is. Okay, based on our definition from above. And with this one, we're gonna employ all the rules we learned about gases and what happens when they expand adiabatically, using things like specific heat capacity and some of the relationships that we got that involve gamma, the ratio of CV over CP, if you remember that. Okay, so let's look at this process and try to understand what's happening here. So the picture on the left corresponds to the graph on the right. So let's just go one by one for each of these processes here. So 1 is the adiabatic compression stroke. Okay, so it's called the intake stroke. It says the piston moves down, causing a partial vacuum in the cylinder. And the partial vacuum in the cylinder, I believe it pulls this valve inwards here. So this valve is kind of free to move up and down. This is one cylinder, right? If you have like a V6, you've got 6 of these in your car, all operating off the same crankshaft, right? Okay, so the piston moves down, causing a partial vacuum in the cylinder, and that pulls in the gasoline air mixture. In your car, it doesn't just burn gasoline, it has to burn gasoline plus air. So gasoline air mixture enters through the intake valve. Okay, and so where is that here? That's the adiabatic compression stroke. So you're moving from, we could write on here, I think this is A to B, right? The volume goes from some volume, which is R times V. R is the ratio of the large volume to the small volume. I guess I could write that somewhere over here. So R is ratio of volumes. So this is AB right here on our picture. So what happens to the pressure? The pressure goes up, right? The volume decreases along this line. And this is an adiabatic compression. What does adiabatic mean? Can you guys remind me what adiabatic means?
the heat, no heat in no, like, it's kind of isolated. Q is 0.
Q is 0, that's right, yeah. Adiabatic, again, means that there's no heat transfer that occurs in this process, and in order for that to be true, um, the this has to happen very quickly, right? All right. Actually, this is... Wait, I got it wrong. It's not A to B. What is it? Isn't this like B to A? Yeah. So why does it go this... Why is the arrow this way on the picture? Maybe because it starts at a different point?
It's going down, or the... Oh,
Yeah.
this whole system.
So look, the thing that says it's going this way, right? So the piston is...
Yeah.
The piston's going downwards, and it says it's a... Huh. Looks like it's B to A. Let's keep going with this and see if we can follow what's going on here. 2 is heating at constant volume. Compression stroke. It almost feels like these numbers here...
Yeah, it
they
actually
don't
looks
see-
like it would
What's up?
go to B to A
Hmm.
for the first part.
I'm just starting to think that these numbers on the left they don't compare to the numbers on the right. Does that seem right to y'all? Because if we look at these one by one, this says adiabatic compression, right? And adiabatic compression is number 2. So I think we fix this a little bit. Maybe I'm wrong. I think this is number 2. Do you all agree? Yeah, they're meant to be read separately, but they're on like the same page, unfortunately. So, I mean, see, it's like they follow right after each other. I think you're right. We can compare them though, right? So this is what we call number 2. This is A to B. We can agree with that, right? This is A to B. Okay, so this is AB, which we call number 2, the compressor. The intake valve closes, and the mixture is compressed as the piston moves up. Okay, so compressed means we go from a volume R times V, which would be like the full volume, this would be RV, to a smaller volume, which is V right here. Okay, so that's A to B. Okay, ignition. So now that it's been compressed, a spark plug ignites the mixture. All right, so it compresses here, and then the spark plug ignites it. When the spark plug ignites it, that's going to be kind of energy coming into the system. So this is going to be B to C. Oops. This is B to C right here. There's heat coming into the system. They're labeling it as 2, but this is 3. And yeah, it's B to C. And then there's the power stroke. Due to the fact that it's been ignited, the gas and the air mixture in here has to expand. This is where the energy is effectively coming from, right? So the gas expands outwards, like this, to a new size RV. This would have to be then C to D. All right, that's the adiabatic expansion, or the power stroke. So this is number 4. And then there's the exhaust stroke, where exhaust valve opens on the right-hand side, and the piston moves up, expelling exhaust and leaving the cylinder ready for the next intake stroke. So then it repeats back to number 1 right here. Right, so it pushes upwards this way, and it expels heat out this way. So that's going to be from D to A, and now we're set to go back to A again, basically. And in this process, from D to A, you've got heat coming out right here. So we're going to investigate each one of these steps. Cooling at constant volume, or the cooling of gases. This would then be probably back to, this is 5, right? Exhaust stroke. This is like 5 and 1, basically, I believe. Up and then back down. And part of what's driving all of this is, maybe I'm wrong. Maybe some people in here know more about how these engines work than I do. But for example, in the process from C to D, where the gas ignites, right, it causes it to expand. So now that it's expanded, this crankshaft down here, it gains kinetic energy and momentum, right? So that momentum basically carries it back around in a circle and effectively forces the gas to expand like this again. But then the crankshaft is again going to have momentum, and it's going to carry it this way to automatically get back to this process here. Is that right? Those of you that know more about how these engines work. Is that the momentum of the crankshaft helps to keep this process going in cycle? right? Like the only thing that's happening with the gas itself naturally here is that the gas is compressed and then it's fired with the spark plug, and then that expansion is where the work is being done, right? But then I think that you'd ask, like, why does the process continue? I think it's because of the momentum of the crankshaft or the inertia of the crankshaft. Does that seem reasonable? Sure. Are you actually convinced, Baron, or what do you think? I'm mostly asking, like, what you all think about that, if that seems like physically reasonable to you. Should I say it again because maybe other people don't understand? I think Baron understands what I'm saying. Maybe other people don't. I'm just saying that, like, in order for this process to actually drive your car, it feels like there's really only one place where you're getting energy, right? It's this stroke right here is the only place where you're gaining energy from the gasoline. Would everyone agree with that? Okay. So given that that's the case, the entire rest of the process has to come from that energy input, right? And that's the idea of what a heat engine is, right? You get heat in, that's the BC process, right? Heat's coming in right here. And then some heat goes out, but the fact that there's a difference between those two and the fact that the process operates in cycle means that the area of this strip here gives you the work that's done. But really, this is the only place where you're getting work in, and everything else kind of carries out through kind of natural processes, as to say the momentum of the crankshaft and stuff like that, that's carrying it around. Okay. Anyone have any questions or comments about this? So let's look at the mathematics of this, and our goal here basically is to kind of ask this question: what is the efficiency of this engine? What's the efficiency of this engine? All right. So in this process, what we have happening is that the gas expands from some volume V to some volume R times V. And again, R is just the ratio of those volumes. R might be on the order of, let's say, like 8 to 10 or so, or something like this. So it's either going to expand to about 8 times its volume or about 10 times its volume. And that's where the kind of work that's going to happen in here is going to happen. All right, so if we look at the process of B to C and the process of D to A, both of those processes occur at constant volume. And because they occur at constant volume, maybe what we can do is we can just take this diagram here now and move it down as we do this. We'll probably do that. Then we can actually say that the amount of heat that comes in QH, right, should be equal to the number of moles of gas that we have in the system multiplied by the molar heat capacity at constant volume, and then multiplied by the temperature difference. So we're just going to say the temperatures at each of these points are going to be like TB, TC, TD, and TA. So we multiply by the final temperature, which is TC, minus the initial temperature, which is TB. Okay. So this is the initial temperature TB right here, and it goes up to TC right here. QC, the heat that goes out, should be equal to something similar. Again, it's constant volume. Constant volume because this is a PV diagram, right? So pressure on the y-axis, volume on the x-axis. A line that goes straight down represents constant volume. So the heat QC that's expelled is going to be N multiplied by, it's the same air-gas mixture here, and then multiplied by final temperature, which is going to be TA, minus the initial temperature, which is TD. Right? All right. So we know that the efficiency of our engine can be given by QH plus QC divided by QH. This is kind of similar to what I wrote above. The only difference is there's a plus sign now. And that's because QC is just automatically going to be negative. The idea here is that TA is going to be less than TD. But we're going to leave it like this because we need to do some math with this. And we'll put the absolute value signs on earlier. So the only difference here is above we said the efficiency was equal to QH minus QC. But remember, this was equal to work. And the work was equal to Q, which was equal to this, as it says in the picture right here. It's QH plus QC, with the understanding that QC is going to be a negative quantity. All right, so we've got that. The efficiency is equal to that. So according to these things right here, then, I believe if we plug both of these into, I guess we'll just do it without. Both these terms have N times CV in them. So it's NCV times TC minus TB plus NCV TA minus TD. And we divide all of that by QH, which is this one. And the NCVs cancel out, and we end up getting, in the numerator, TC minus TB plus TA minus TD divided by TC minus TB. Now, we don't know much about these temperatures without actually investigating a specific engine. So what we can do is we can look at the other two processes here. Let me move this down. I didn't think it was going to work. We're just going to have to pull this down without keeping our little pictures there. So now let's look at the other two processes. The other two processes are from A to B and from C to D. These are adiabatic processes, right? Adiabatic compression stroke and adiabatic expansion power stroke. And what we learned is that for adiabatic processes, so which are these? This is A to B and C to D. And in adiabatic processes, what we know, I believe, is something like this, that if I take temperature 1 times volume 1 raised to the gamma minus 1, that this is equal to temperature 2 times volume 2 raised to the gamma minus 1 as well, where gamma is the ratio of CP to CB, right? So in our case, if we're doing the A to B process, then we're going from temperature A multiplied by VA times gamma minus 1 should be equal to temperature B times volume B times gamma minus 1. But we know that in our process, there's a ratio between VA and VB such that, let's see, VB is, okay, we can see it on a picture right here. This is going to correspond to V sub A, and that's going to be VB. VA is the larger value, right? So what we can do is we can write, instead of VA, we can replace this with temperature A multiplied by R times VB, because V is equal to VB. Sorry, you can't really see it right there. Raised to the gamma minus 1. Now I think we can eliminate the VB to the gamma minus 1 from both sides. So this is going to say that TA times R to the gamma minus 1 is equal to TB. Any questions about that? So this is the process of A to B. The other process we need to deal with finally then is from C to D, the compression process. So for CD, what we'll get is, we'll skip the first line and just say we're going to get TD, which is the final, at R times, well, it's the same VB, right? We can call it VD if we want to, but I guess we will just to be, no. What's the best way to write this? It's R times VB, right? Yeah, okay. what I would say above this is that VD on our picture right here is the same as VA, which is equal to R times VB. That's why that shows up there. And then VC is just going to be equal to VB. So we'll write this one as TC times VB to the gamma minus 1. I guess I could have everywhere there's a VB, I could just replace it with volume. I don't know. Again, the VBs cancel, and we end up getting TD times R to the gamma minus 1 is equal to TC. So we've got this equation. We've got that equation. And now we're going to do some math. We're going to plug them back into this equation here. Because we can now eliminate TB and TC and just have temperature A and temperature D. And that should allow us to get this entire temperature ratio thing down to just something that has gamma in it and R as well. All right, before we do that, does anyone have any questions? Are you all, have your brains glazed over from staring at math? Early on a Monday morning? Okay. All right, so let's plug these things in. So anywhere we see, what's the easiest way to do this? Anywhere we see a TB, we're going to write TA R to the gamma minus 1. And anywhere we see a TC, we're going to write TD R to the gamma minus 1. Yeah. Okay. Let's see if I can do this without scrolling down too much so we can keep everything together. So TC, so this, remember, this whole thing is equal to efficiency, right? That's what we're calculating. Efficiency, just to bring things back home, is now going to be, let's see, TD times R to the gamma minus 1, replacing the TC. Replace the TB minus TA R to the gamma minus 1. We leave TA the way it is, so plus TA minus TD. Hopefully this will work out. In my notes, all I wrote was, I wrote the stuff here, then I said math, and then I wrote the final answer. So we're going to see if it works out. The denominator was TC minus TB, so we need to replace both of these. TC is TD times R to the gamma minus 1 minus TB. So TB is this one. TA R to the gamma minus 1. I think this worked out well, because I think every single term has TA, well, not every term, but like this. This term, and this term. Make sure I did it right. Hold on a second, let me look back up here real quick. QH was TC minus TB. Did I copy that down right? Yeah. So the denominator looks like it has the opposite sign, but there's a TD minus TA right here. There's a TA minus TD, and then a TD minus TA right here. I think it's going to work out, but I'm a little worried that this is TD minus TA, this is TD minus TA, but this is the opposite, right? TA minus TD. I guess that's okay because this was technically supposed to be a negative value, right? Because it was the QC. I think we're okay. All right, so let's take this then and let's do the following. Hopefully this isn't too confusing. Let's rewrite this one. TA minus TD. Let's change it to negative of TD minus TA. So I changed it because this has a TD minus TA, this has a T, everything has a TD minus TA now. So that we can write this like this. This is going to be TD minus TA divided by TD minus TA, which is obviously equal to 1. So the numerator part is now going to be multiplied by, looks like R to the gamma minus 1, minus 1. And the denominator is just going to be R to the gamma minus 1. Okay, I think this actually worked out. Can you all follow that algebra? Every term has TD minus TA in it. So we factor TD minus TA out of this term, and you're left with the common factor, which is r to the gamma minus 1. And then you factor TD minus T out of here, and you get a negative 1. Same thing on the bottom. You get r to the gamma minus 1. These cancel.
Yeah, that's all clear.
That looks good? Okay. And then what we have is r to the gamma minus 1 over r to the gamma minus 1, but we can write that a little more simply as E efficiency for the Otto cycle is going to be r to the gamma minus 1 over r to the gamma minus 1 is 1 minus 1 divided by r to the gamma minus 1. Now, this is the way your book puts it. I don't like the way this is written. I think we can write this in a more simple way. But here, this is what your book puts. This is going to be the efficiency of the Otto cycle. It's kind of an idealized efficiency because there's an assumption or two that we made that are, yeah, that's how you would write it. I like that better too. You could write E equals 1 minus R. See, when I write R like that, it looks like a gamma. I gotta be careful. R to the negative gamma minus 1. But even this can be written more simply, right? Because you can just factor the negative sign inside of it. It would be E equals 1 minus R to the 1 minus gamma. I like that one better. God, my R's and gammas look really similar to each other. I apologize. Anyway, so let's get some actual values of these things. So if we use... Why didn't I write down gamma? What I wrote down is that if... Let's try this. If R equals 8 and we use gamma for air, I think gamma for air is like 1.4, right? If you use those, what do you get for E? Can you all calculate that? Where's my phone? Oh. Can you all calculate that and tell me what you get? Yeah, I guess that's right because I got the same number the book did. Yeah, 0.56, so 56%. 56%. Every time I pick up my phone, I lose my writing utensil. Oh, there it is. So you get an efficiency if you take a... So this is the compression ratio, right? R was, just to kind of bring this all back, R was the kind of ratio of the final volume to the initial volume in the process, and we end up getting that E is about equal to 56%, right? In reality, for most internal combustion engines, the efficiency is actually closer to 35%. Does anyone know why there'd be a difference between... This is like the ideal efficiency. Because there's some assumptions we made when we went through this process here, right? That are just not accurate, right? Does anyone remember what they might have been? What are some of the things that would cause the real efficiency not to be quite 56%? And by the way, this would be a really, really efficient internal combustion engine. What is it? What are some of the assumptions that we made here? I think you can see it from the picture, actually. What are some of the assumptions that were made here that are just not accurate? Constant volume? You're saying that the gas might not be truly at a constant volume while that process is happening. That's probably true. Probably in reality, there's some slant to these curves here, either that way or this way. Probably the latter. Probably the like as the heat comes in here. It probably expands a little bit when that happens, right? And when the heat goes out, it probably maybe that way. I don't know. Okay, what else? There's a much bigger one. I think you're right though. That constant volume is part of it. So probably the like using this equation is probably not exactly 100% accurate. It's probably only an approximation. There's another big one too. What's the other one? What about the other two strokes? Is there anything unrealistic about our assumptions for this stroke and this stroke right here? What's adiabatic mean again? No heat exchange. Do you think
Like no heat exchange.
Do you think that's reasonable? What would have to be true about our pistons in order for there to be no heat exchange with the environment?
I guess like
Yeah, the walls would have to be perfectly insulated. That's right. And the piston, as it slides, would have to be perfectly lubricated so that there was just absolutely no friction, because friction is also going to generate some heat that we're not going to be able to use in the system. And yeah. So I wrote down friction and then heat loss to the cylinder, which would be those two main things. I would assume some of the energy associated with sound is not contained within the system too, right? These machines, they make noise, which means there's some kind of energy getting out of the system too. Although it might not be very much. Mostly it's probably just friction at the end of the day. Friction within the crankshaft, right? That's got moving parts, the piston itself, all these things. So apparently that has a pretty big effect, because a 20% difference is pretty huge on a scale of 1 to 100. All right, so that is an example of a heat engine. A heat engine that has as its working substance gas and air, and it has the effect of burning the fuel and then using the burning of the fuel to expand a piston, and then the expansion of that piston does work. And the amount of work that it's able to do is dependent upon, Anyway. One thing I didn't write down, I believe, is that there are some limitations to this process. So one thing that we could say, so I guess there's an argument for why this piece right here is nice to be written the way that it is. If you wanted to make it more efficient, would you want a bigger value of R or a smaller value of R? Like if R was 10, you can do the calculation yourself. If you use R equal to 10, do you get it to be more efficient or do you get it to be less efficient? Or can you just tell from the equation?
should be more efficient
And why do you say that? How do you immediately know that it should be more efficient?
because of the negative exponent.
Yeah, negative exponent, exactly. R is the denominator. Gamma minus 1 is always going to be some number that's positive, basically, because gamma is generally like 1.5, 1.3, something like this, right? So this should lead to an efficiency that's greater. Let's see what it is real quick, just because let's have a number. Let's see how much more efficient it is. So I guess as I'm calculating this, I would ask the question, do you think there's a limitation? Why don't we just make these things so that they have a huge value of R? Again, R is the ratio of the volumes, how much it expands, basically. Yeah, it ends up being 60%. It's not much more, but it's a little bit more. So your book mentions something about if it becomes too large. What did they say? I'd have to pull the book back up real quick to remember what they said. Something about you could cause the whole system to explode or something like that. I can't remember exactly what they said now. Here, it's back here. Internal combustion engines. Here it is. So the efficiency can be increased by increasing R. However, this also increases the temperature. Yeah, it increases the temperature at the end of the adiabatic compression of the air-fuel mixture. If the temperature is too high, the mixture explodes spontaneously during compression instead of burning evenly after the spark plug. So I guess that during the compression part here, if it goes from too large a volume to too small a volume, it will just automatically ignite, and that prevents this kind of even expansion that they expect. And it says this is called pre-ignition or detonation, and it causes a knocking sound and can damage the engine. Octane rating of a gasoline is a measure of its anti-knock qualities. The maximum practical compression ratio for high octane or premium gasoline is about 10 to 13. So I think this is why I've never believed much in this, but like when you buy certain types of automobiles, they'll say that you need to get premium fuel. Do you guys know what I'm talking about? There's certain types of, I'm assuming this is why. It's probably because they're using a very large, Audi does it. Yeah, I think BMW does as well, a lot of German cars. I'm assuming it's because they're probably using a larger compression ratio, which means that you need to have gasoline that will not ignite whenever the compression process happens. Have you ever heard this knocking sound before? I've never heard this knocking sound.
The knocking, yeah, it does exist.
You've heard it before?
Yeah.
Really?
It's typically like in an older car.
Okay. They call it ping, Delvino? Maybe. Yeah, maybe so. Maybe so. Okay, this is a pretty good place to stop. We'll come back and we'll talk about refrigerators here in about 10 minutes or so. And continue to talk about the second law and Carnot cycle, all that kind of stuff. So we'll take a break for 10 minutes and we'll come back.